Good morning, this is Christina Long and this is the Science 411. Today's video is just a simple walkthrough of some nuclear chemistry notes. Alright, so nuclear chemistry is not the same as other types of chemistry that we have studied. There are a few notable differences. Number one happens when bonds are broken and formed. They use only valence electrons and they have small energy changes. That's a big deal. It changes part of the atom, but the element stays the same. Temperature, pressure, concentration, and catalyst affect reaction rates. Now, we dealt with that earlier, so you should understand that. Things that classify nuclear reaction. It happens when nuclei combine, split, or give off radiation. It can use protons, neutrons, and electrons, not just valence electrons. They have very large energy changes. Atoms are sometimes changed into atoms of other elements, and temperature, pressure, and catalysts do not normally affect reaction rates. So there are some noticeable differences there. So in the history of nuclear chemistry, you've got Wilhelm Röntgen, Henri Becquerel, and then Marie Curie. And if you look and read through all of those, they kind of tend to roll one right after the other. And Marie Curie actually did a lot with Henri Becquerel's work, and you guys can read that on your own, but it's interesting stuff. So radiation, what is it? It comes from the Latin word radiare, which means to radiate, and radioisotopes are isotopes of an element that have unstable nucleus or radioactive element. Why are things radioactive? It's basically things become radioactive. They are radioactive when they give off materials. They're unstable, and they give off radiation to become more stable. So if you're looking down at the bottom picture, you've got this block, whatever that happens to be, and at that point it's unstable, because normally the larger things are, the more unstable they become chemically. And if it gives off radiation, in whatever form it ends up giving it off, it becomes a more stable molecule. It becomes a smaller molecule. And if it doesn't give off radiation, it remains unstable. So there are three main radiation types, and you've got alpha radiation, and it really looks like a helium ion, which really doesn't exist in normal chemistry. It's just a helium atom where it's lost two electrons. Alpha radiation is a relatively large piece of radiation. It can be blocked by paper, and it can be slow moving. All right, and then you've got your reaction there down at the bottom. So you've got radium-226, and you've seen this before, hopefully. But if you haven't, understand that when you've got that radium-226 there, it's still the same thing as that. This is just giving you the mass, and so is that. So it's just reminding you what the mass numbers are. Okay, so radium turns into radon. Not only does it change mass, it goes from 226 down to 222. Well, the difference in that is 4, so that's where it shows up in that helium. But also, it goes from 88 protons to 86 protons. Well, when you lose 2 protons, it becomes a different element, and that's why it becomes radon. And again, those two protons lost are picked back up in that helium. Alright, it's got a very low penetrating power. It's got the, again, it's because the molecule is really large. And it's not very strong. You can block it by a piece of paper, and it is very slow moving. Alright, so as far as penetrating power goes, alpha is the least strong, and then you've got beta, and then it goes down to gamma. Alright. There are two more forms of radiation that you need to be aware of. Beta radiation. Beta radiation are essentially, or beta particles are essentially electrons. And that's important to know. They are very fast. They can be blocked by metal foil. So in some old school 80s movies, sometimes the crazy guy is walking around with aluminum foil on their head. And the reason they're doing that is because they're trying to block beta radiation. Alright? Beta radiation does have a negative charge, so if you look at that reaction down below, you've got iodine, you've got 131 iodine, and it picks up a proton and it changes to xenon, but it gives off a beta particle. And basically what it does is it converts a neutron into a proton. So gamma radiation, these are photons, energy only. Now this is a big deal. There are no particles with gamma radiation. It's just energy. It has no charge. It's got high energy electromagnetic radiation. It's pretty much the highest electromagnetic radiation. It goes along with alpha and beta. Not always, but most of the time it is. And it is not completely blocked by lead or concrete. And that's kind of a big deal. You can't really completely block gamma radiation. You can slow it down and you can absorb it, but it's pretty harmful stuff, and it's hard to stop. Alright. Particle review. You've got alpha, beta, and gamma. And alpha looks like a helium, beta looks like an electron, and gamma is energy only. Now, there's some newer science stuff, and if you're a science fiction geek like I am, Star Trek is... these are two terms that showed up in Star Trek, I don't know, a long time ago. But the term positron and neutrino, those are real. So a positron is an opposite electron. It's considered to be the antimatter of an electron. And then a neutrino is a small elementary particle with no charge and virtually no mass, and these have antineutrino particles also. That is past what you would be called your pay grade. You won't have to deal with those in this class. Alright, what is it? Okay, so you've got more decay types. You've got a positron emission, and then you've got electron capture. You can look at those again. It's not really anything that you need to know for this class. Then you have something called radioactive decay, and on Tuesday's video I'm going to deal a lot with practice problems on radioactive decay, but it's dealing with half-life, and it's the time required for half of radioactive substance to decay. So if you take a look at what's written in blue, you start out with 100 grams of cobalt, 60. And it's telling you in that little arrow that it's got a half-life of 5 years. So every 5 years, the substance cuts in half. So when you're looking at it, you got 100 grams, and it goes 5 years, and then it turns to 50. Then it goes another 5 years, it goes to 25. Another 5 years, it goes to 12.5. Every half-life, the substance cuts in half. Right? It's one of the best named things in science because, well, it actually tells you what it is. Now there's some nuclear reactions. Einstein's equation is E equals mc squared, which you guys have seen, I'm sure. E equals m is for energy, m is mass, and c is speed of light. Now, speed of light used to be thought of as the fastest thing in the universe, and then they found out that electrons travel faster, so that changed, changed things up a little bit. But that's still the equation. And then you've got nuclear fission versus fusion. Fission is splitting of an electron, and it's used in nuclear reactors. It gives off a great deal of nuclear waste or gamma radiation. And then you've got nuclear fusion, which is the combining of atoms, and as far as we know, it's used in the sun, and it does not have radiation that is given off. But we haven't figured out how to do it. And you've got a picture of a nuclear reactor. Shows you how the water cools everything down, but basically it's still running like a turbine. They're using the the energy given off in the nuclear fusion to still heat water, still run a turbine, and create electricity. And then you've got nuclear fission, which is the reaction that's going on in that reactor. And it's the splitting of an atom, and it's used in power plants, uses uranium-235. And if you look, the blue ball basically that hits the uranium-92, that's a neutron. And when it hits, it basically breaks it apart and makes it into some other things and gives off neutrons, and there's a lot of radiation that goes along with that. There's something called a chain reaction. It's a self-sustaining process in which one reaction begins the next. So if you look over on the left, that's where the reaction starts. And as it gives off particles and gives off energy, it uses enough energy to start more. Nuclear fusion is the combining of nuclei of atoms, aka thermonuclear reactions. It requires a temperature of 5,000 Kelvin, which is pretty darn hot. It can be done in nuclear explosions. It's used to power the sun. It's not been achieved trying to use magnets to contain it. Hopefully, future power source. Again, 80s, lots of 80s science fiction movies are all talking about nuclear fusion, which, again, that's been a long time ago and we still haven't figured it out. So hopefully soon. So, that's just the general stuff on nuclear chemistry. Next time, I'm going to be dealing with half-life and walking you through that, so that should be a little more entertaining. Hope you guys are doing well. Remember to make good choices and clean your room. Have a good day.